We're going to take a look at this thing, the bell-shaped distribution. So the nice symmetric curve. So we're going to collect real continuous data and we put it in our histogram. You'll see this pattern, something like that. But you'll notice that, so basically it's got the modal class. You notice they're classes rather than individual discrete pieces here. It'll be somewhere in the middle of the range of values. If we've got that sort of distribution, and it's sort of symmetrical. You know, it comes from a low point up to a high point, back down to a low point again. The perfect symmetrical distribution, the bell-shaped curve, is this one, where the mean is actually equal to the median and it's also equal to the mode as well. Those three key pieces of data are the same. And that's when you've got a perfectly symmetrical probability distribution. The example I got on the left there, it's not symmetrical, but it's almost symmetrical. The frequency density tails off rapidly as we move further away from the mode. That's the key thing we're looking for. So it's nice and high, but then it tails off. Because the normal distribution, I guess, is, for want of a better word, the perfect one. So a random variable x, if it's probability density function, and there's the formula for it. Don't panic, we're not going to have to integrate this. But if the coefficient there you'll see is 1 over the standard deviation, root 2 pi e to the power of minus x minus the average squared over 2 times the variance for all x. That is what we call the normal distribution. And how we write it down in notation, we say x, our random variable, then we just use a tilde. N, so we're saying it's normally distributed. So that's what n is. And then in the parentheses there, we put the average and the variance. They're the two key pieces of information that we want. So what are our characteristics? There it is, the lovely curve. It is an even function. We've got that symmetry around the axis. The maximum is the mode, is the mean, it is the median as well. And again, symmetric about the average. The points of inflection occurs at one standard deviation away from the average. So that's the point of inflection. So we're now interested in the standard one. So there's lots of data that will be normally distributed. The standard one is this one, where the average is 0 and the variance is 1. Now that might sound familiar to you. Z-scores. Remember all the Z-scores I'll give you? Those Z-scores are all based on an average of 0, a deviation of 1. So what I've basically done is I've normalized your test scores. And there's the formula when that happens. I now know the average is 0 and the deviation is 1. It simplifies the formula a little bit. It's now 1 on the square root of 2 pi e to the power of minus, and notice I'm even using the pronumeral z now, z squared on 2. So how do we calculate the probabilities then? Yes, it is the integral of that, but we don't actually have to integrate it because that is an incredibly hard thing to integrate. It would be nice if there was a z as a coefficient out the front there, but we haven't got it there. So here's our cumulative function. We represent with the Greek letter phi. So that's phi z is equal to, and as we saw yesterday, probability of z being less than or equal to a certain amount. It's our cumulative function. And there is a graph of that cumulative function for the normal curve. So it starts shallow, gets very steep, and then ends up shallow again. So integrating it, which as I say, I'm not going to get you to do. In fact, here's why it's not, because you can't do it. Not using the functions we know. Really, we're limited to algebraic, trig, exponential, which also means logs as well, those functions, and the integration methods we know, we just can't integrate that. But as I say, fortunately, you don't have to. Right? We're interested in a definite integral, so we don't actually need to come up with the function. We're just interested in the answer. And because we're bringing it down to a standard one, it's going to be the same answer every single time. So we use tables of values. And we can just look up at the table. Someone's already worked it out for us. We can look up the tables for different values. You can estimate, if you like, using the trapezoidal rule. And I know how you love the trapezoidal rule. That's what I was saying. As it's a standard one, they've been done for us. There's a very cut down, small version of the table. So if I wanted to work out the probability of Z is less than or equal to 0.25, or another way of saying it, it's our function 0.25. I can go over to my table and I go, well, there's 0.2. I'll go along to 0.05 where they intersect. Okay, 0.5987 would be the probability. So using the table, here's some rules that helps us manipulate. So there's the first one. Probability of Z is less than or equal to Z. Yep, it's our cumulative function. We just read it straight from the table. Now, we can manipulate. The function negative Z will equal 1 minus the function Z. That's just basically the complementary event idea. If you want to work out Z greater than or equal to Z, then it would be the function negative Z. Because remember, you're dealing with a symmetric graph. So you've got Z and you want just the top half. Because it's symmetric, it's going to be exactly the same as if you go negative Z and bottom half. So you can do it that way, and then you could read off the tables. So if you want to work out in between 2 points, then you just subtract the two function values. And the final one I've got there, if you want the absolute value, then we go twice that value, but we subtract 1. Now, if you happen to have a 100 AU, then you're in luck. If you don't, enjoy looking up the tables. Now, 100 AU. Mode 3. Got your calculators? Get them out. Mode 3, AC, so all clear, but that will put the calculator in statistics mode. On some calculators it says SAC, statistics all clear. Shift 1, 5. That will bring up standard normal distribution menu. So shift 1, 5. Now what you're basically doing, it has 3 functions there. It has P, Q and R that you can choose from. P is the one I've just been talking about. It's the cumulative one going up to the point. Q will tell you from 0 to a point. And T basically gives you the opposite of P. It gives you the top part of it. So there are 3 things it can find for you on the calculator. So if I want to work out that one we did before, the 0.25, I'd simply go 1, because I think that's how we get the P, was 1, wasn't it? So press 1 for the P, tell it the number. No, don't type negative 0.25, that's 1 dash 0.25. So type in 0.25 and it should work out that, which 0.59871 actually does it a little bit more accurate than the table of values that we had. Those of you who do not have a 100 AU, do not panic, because when they write something like an HSC, they have to have it what's called technology neutral. So it should not matter what calculator you're bringing to the exam. Everyone should be on a level playing field. So what they do with these sorts of questions is the answer will come up to be a nice number. So it might be 1 deviation from the mean, 2 deviations from the mean, which you remember those empirical values, and the graph is even on the reference sheet. So, okay, we know those, how many percent are in those. Or they will put the table in the exam and then everyone can look up the table and you use those values to solve it. But as far as working on in our exercise, if you want to use the calculator, you can use the calculator. So, let's see if we can do something. We want Z less than or equal to 0.44. You should get 0.67003. If you want Z is less than or equal to minus 0.81, then I would go 1 minus, and then I'll go to my calculator, work out what the answer is for 0.81, and we'll get 0.20897. Other way you could do it is you could just go straight, because notice it's still going less than or equal to minus 0.81. With a calculator, you could just put that straight in, minus 0.81. See, with table of values, you couldn't, because the table of values only has positive numbers. So you would have to use this rule to convert it. So I can read off the table the 0.81. So you'd have to go 1 minus that one. In between these two values, okay, well, it's going to be 0.94 minus negative 2.34. Again, that negative one, if you're reading off a table of values, you're going to have to go 1 minus and then 2.34 to get that number. But if you've got the calculator that will do it, you can plug that straight in. Absolute value in between 1.15, so I can use that rule. It's 2 times the 1.15 minus 1, and we'll come up with that value. I mentioned it just before, the empirical rule. Let's have a look at it again. There it is. You should find one deviation from the mean, 34% of the data, so 34% either side. So 68 all up, one deviation from the mean. Then there's another 13.5% in between 1 and 2 deviations. Then between 2 and 3, 2.35%. So you pretty much capture all of the data in 3 deviations. So if you ever get a z-score which is less than -3, because there's only going to be about 0.15% of the data out there. Mind you, if you get one that's bigger than 3, you're doing real good, because there's only about 0.15% that way. So that's for a normal distribution. So 68% in one deviation, 95 ends up between 2 deviations, 99.7% of the data, 3 deviations. Okay, so that's our normal distribution. And then tomorrow we'll look at how we play with our normal.